So let's start with, so I'm going to talk about L1 full groups of flows. Actually, I should have been a bit more precise. I want to focus on PMP flows, so probability measure preserving. And in this first part, I also want to tell you about PMP bijections. I'll start by PMP bijection. So for me, X mu, as always, is a standard probability space. In this talk, we're going to do measured dynamics, so everything is up to measure 0. But feel free to interrupt when you feel like I should be more precise in my statements. And also, every maps, every set is going to be measurable. Okay, and so the first definition is that of a PMP bijection of, so our standard probability space X mu. So this is T from X to X, well, which is a bijection. And being probability measure preserving, this means that for every A in X, the measure of A is equal to the measure of T of A. All right, so let me recall two examples for those who were not there last week. So the first is irrational rotation. So here my space X, I can take it to be, if you want, the 0-1 interval. Oh, sorry, trying to speak English, write English. It's not easy. So, and then you take theta irrational, and you have this transformation T theta, which takes X to X plus theta modulo 1. This is first example. Second example, I guess they were somehow already mentioned, but let me just recall that we have these Bernoulli shifts. So here, for instance, you take X to be the pair 0, 1 to the Z, and then T of X of a sequence Xn is the sequence Xn minus 1, which corresponds to shifting your infinite sequence by one step to the right. And I should also tell you what the measure is. So let's take 1/2, 1/2, and independent like this. So these are my two examples. And now I want to tell you about flows, which will be the main topic of this talk, and the connection with PMP, between PMP transformations and flows. So first, a flow, and I mean, here I should add the keyword PMP, is an action of R on X by PMP bijections. Okay, and the first example that I want to give you is I still have an irrational theta, but now I take X to be 0, 1 times 0, 1, or if you want, the two torus, with, or here I should have said this is with Lebesgue measure, of course. So here, measure mu is, again, I use the Lebesgue measure. And now let me just maybe draw a picture. So this is my square. And I can say I have a point X there. And I want to describe the flow. So really you can think of this as just drawing lines, a flow, and it's going to do something like this. This is part of the flow. So it goes like this at, say, unit speed. And when it reaches the top, I want it to arrive at, let's say, X plus theta. Okay, so then my flow continues like this. Then it goes here, then back there, etc. Okay, so I could give you a formula, but there's, I guess this is pretty clear. So this example somehow is quite nice when you want to understand the relationship that there is between probability measure preserving bijections and flows. So its key property is that I have a set here. Let me call this set Y. So Y is just singleton 0. No, that's not how products work, sorry. So interval 0, 1 times 0. And you see that this set intersects every orbit in a discrete subset, okay? And actually the distance between two consecutive points, it's something like square root of 1 plus eta squared or something. So now I want to build on this example and tell you, and I mean, yeah, the key point that I want to make is that you really have here a probability measure preserving transformation, I mean this irrational rotation, which, as you see, is related to this flow. So let's see the general construction. So general example. We want to start from a PMP bijections and build a flow. So we start with T, PMP bijection of a probability space Y nu. Okay.
So when you say intersected discretely, you mean
not
the image in R is discrete, not?
So I'm saying that if you think of what happens orbit by orbit, each orbit is a copy of R, the action is free. And when you look at the trace that this set gives you on this orbit, you have points which are spaced by this amount. Okay?
In R, not
in R. Yes.
Yeah, it's a little confusing because on the pink it's not discrete.
Yeah, on the pink it's not discrete.
Yes,
but on the R.
Yeah, when you look at the orbits, and this will be an important point, each orbit identifies to a line, and understanding, the local picture that you have on each orbit will be a key thing. Okay. Other questions? So now I want to make this more general. So how can I do this? I have this PMP bijection. I'm going also to take some f from Y to positive reals, and I want that its integral is finite. Okay. And now let me actually tell you this story in a kind of formal but nice manner. So I will consider a space that I want to call X tilde, which is Y times R, endowed with the product measure. So this is an infinite measured space, okay? But now on this infinite measured space, I have two natural things. I have a transformation T tilde, which does the following. So it sees a point Y and a real T. It's going to on the Y coordinate, apply T, and on this coordinate, add this function f of Y. Okay, and so, maybe I should just throw this here. So I have Y, and now I have this very large band, and I have this first transformation, which goes up and also moves by T. And I have a commuting flow, which is an infinite measure preserving flow, so which is just, let me check here, I'll write it, alpha tilde of T, alpha tilde T of Y T prime. It's just, well, don't do anything on the first coordinate and add T prime. Yeah, I forgot to say it. Flows, usually I will write them as alpha or maybe beta, and alpha T is what you're doing, the measure preserving transformation, which tells you what's going on at time T. Okay, so these are two transformations, and you see that this flow commutes with T tilde. So this tells you that this is a coupling between a measure equivalence coupling between R and Z. And the point is that as soon as you have such coupling, so two commuting actions, then you have both groups which act on the space of orbits of the other. So here the T tilde action on the space of orbits of alpha tilde, it's just my original T actually. But the interesting thing, if I want to build a flow, is that now alpha, so alpha tilde T acts on the space of T tilde orbits, so which I will denote by X tilde over T tilde. And this is actually a finite measure preserving action. So what do I mean by this? I mean that, I can represent my function f as something like this, and I have a nice natural fundamental domain for the T tilde action. This is this space here, which maybe I should use colors. This is a set Y. So all this thing. This space Y intersects every orbit, so at exactly one point. So I get really a flow on this space Y, which is endowed with the measure induced by this. So in order to get, so what's the total measure of this guy? It's just the integral of f. So then I just renormalize, and I get something which I will write down on the next board. So I write it as alpha TF, which is the flow built under F from, okay. And I can really think of this flow very concretely. If you don't like this quotienting stuff, really what's going on here is I can really view this as, sorry, this should be X. This is the set that I want to act on in the end. This space X, what's the flow doing on it? It's just basically going upwards, like as soon as, you flow vertically as long as you can, and when you reach the top, you just go back here. Okay, sorry, you go back here, but using the transformation T. So like here you do T. Okay. So this is a nice construction, and
the first example, the lines were just
I will
the slopes.
yes,
And all with the same one of tangent, etc.
yes, so maybe I don't know. Okay, so here's a theorem by Ambrose and Kakutani. It's that every,
Is this what people call suspension flows?
yeah, that's also a name that's commonly used. Yes.
Delay suspension.
Yeah. So every PMP flow arises in this manner. And moreover, you can take f greater than epsilon if you want. And I'll just comment on this. So it's then natural to ask how nice can f be? And you can actually take it to be two-valued. This is a result of Feldman from the 80s. And I just want to say that, so Kostya has a very nice improvement of this. In the purely Borel setup, he shows that every Borel flow of R can be represented like this, and with F taking only two values. So that's a recent result of his, which is very nice.
So that's
Okay.
like starting with a Borel T, or yeah.
So you start with a Borel action of R by just Borel bijection, Borel action, yeah, pre-action,
Okay.
and then yeah.
And T, and there exists a T Borel automorphism.
So okay, I was cheating a little bit. This T, yeah, you get this T Borel automorphism, but the point is really that you can find this cross section here, this Y in your set, which so that the return time to this cross section only take two values. And these values, you can choose them. They just have to be rationally independent, actually. That's what he shows. And sorry?
For logic flow, or any.
No, it's for any maybe here. Yeah, I should have added free flow. You don't need ergodicity. Yes. It's really just about building these cross sections. You have a way of. I mean, yeah, I don't want to. I can tell you how it works later on if you're interested, but for now I just want to state this. And I just want to also make precise this arises in this manner. What exactly I mean by that? So this is the definition of conjugacy. So two flows alpha, beta, say on x1 mu1, x2 mu2 respectively. So they are conjugate if you have an isomorphism of the spaces, measure preserving, such that beta t is just obtained by conjugating by this f. All right, so really this is the strongest notion of equivalence for actions. It's just you identify the spaces and then the actions are the same. Okay. So a good example is given by these irrational rotations. So for this irrational rotation, you can check that you have a conjugacy here between this guy here, which, oh, I did not give it a name. Let's call it maybe alpha theta. For example, alpha theta is conjugate to alpha t theta, and then your function is constant equal to square root of 1 plus theta squared, if I'm not mistaken. Okay, so that's the stronger possible notion of equivalence between actions. Something a bit weaker that you can do is called sometimes isomorphism. So alpha and beta are isomorphic if there exists still this S isomorphism between the spaces, but now you also have this thing that you're allowing yourself to use an automorphism of your group. So here my group is R, and I only want to consider continuous automorphism. So this is multiplication done by some non-zero number, and then the condition becomes S alpha t S inverse is equal to beta ct for every t. Okay, so this is the notion of isomorphism of action, which refines, which is coarser than conjugacy. And for the purpose of stating one theorem, I need to introduce one last notion, which we currently call Kakutani flip equivalent. So definition, alpha and beta, two flows are flip Kakutani equivalent. So if now you want to use this previous representation that we had, but you allow yourself to change the function f. So you want the same t, so you want some t in some out of y nu. But now your functions are allowed to change, so you have some f alpha and f beta, such that, so now alpha, let's say, is really isomorphic to alpha t f alpha. And beta is isomorphic to alpha, t f beta. But here I have to put an epsilon. I'm allowed to change time. So where epsilon is in plus or minus 1. Okay. So written like this is a coarsening of the previous definition. This is a small exercise to check it, but sorry?
Epsilon is constant.
The what? Sorry?
Epsilon is constant.
Yeah. Epsilon is constant. Yeah. So this is a notion which was studied in the 80s in particular. It had some very nice development. So I just want to state one result about it. So I should say Kakutani equivalence then just means that you don't have this epsilon. So it's almost the same equivalence relation. So I just want to state that you have a result of Feldman, and then it was refined by Rudolph in the 80s. There are uncountably many flows up to, I mean, you can add the flip if you want. It does not change the uncountability. You can put any equivalence. All right. So that's it for flows. Maybe just one remark is, I showed you how to build any flow from a PMP transformation, and it's actually a kind of if and only if. But you should not think of flows as something which are strictly simpler than PMP transformations. What I want to say is that there are flows which occur naturally, which I don't know much about, but apparently such things appear in physics. And then, I mean, it's more natural to study them this way because as flow themselves rather than through these cross sections business, just because that's how they appear, you know. So, okay. And now I will move to full groups associated to flows. All right. First, I will talk about orbit full groups. So from now on, I want to assume that all the flows are free and ergodic. So free means that every orbit is really, when you use the orbit map, you have each orbit identifies naturally to R, and ergodicity means every invariant set has measure 0 or 1. And so our goal is to associate a Polish group, to a flow, which remembers, let's say, as much as possible. So Polish group, let me just recall that these are separable topological groups on which you can put complete metric. And Polish groups are very nice. They are the best groups in the world. I don't know why I love them, but I love them. So, and one Polish group is this guy out of X mu, which will be my notation for all PMP bijections of X mu. And I really want to look at them up to measure 0. So I identify two bijections if they agree on a full measure set. Okay. And now, so let's try to to associate to a flow some nice Polish group. So this is something that we actually did with Alessandro some time ago. Where am I? Yes. So if you've ever worked with full groups of PMP equivalence relations, then you want to consider the following. If alpha is a flow, we associate to it an orbit full group alpha flow, maybe to make things precise, still on x mu. And we denote it by bracket alpha. This is just all measure preserving transformations, such that for every x, x and t of x are in the same alpha orbit. Okay, and what we shown for this definition. No, X is really the whole flow space. Yeah, I hope I did not miss up. Yeah, X is always the big space. Yeah, you can forget actually all I said about cross sections. It does not matter so much for now. So I really now have a flow on X mu, and yeah. So yeah, that's the definition. So I mean, in other words, you're asking that there is T such that T of X is equal to alpha T of X. So for every X, there is a T such that this happens. They are in the same orbit. Okay, and what? Forget about cross sections. They were never there. I'm just talking about a flow now. I have my measure preserving flow. Think of this thing with irrational rotation that's here. And okay, and I want to associate to it a Polish group. So this is X. I define this. So in particular, I should say that, well, the elements of the flow themselves, the alpha T, this is, well, it's actually a subgroup of this orbit full group. It's actually, I mean, this full group is much bigger, but okay. So, yeah, so one thing that I wanted to mention is result that we obtain, which makes sense in a more general setup when you replace the reals by a locally compact second countable group. So what is this? So these groups, they are abstractly isomorphic if and only if alpha and beta are orbit equivalent, which by essentially die plus this Ambrose-Kakutani, this is actually always true. So we thought that we had a group which captures many things. Actually, it does not. We only built one group, which is the same for every probability measure transformation. Sorry, every PMP flow. Okay?
Abstractly, you mean forget that.
Yeah. And yeah, I should say, yeah, maybe I should not have said that these were going to be Polish. I wanted it to be a surprise, but I messed up. So yeah, what I was about to tell you is just one more thing about full groups before I define L1 full groups. We can associate to every T in the full group of alpha what we call a cocycle, and these are exactly the same as in Amandine's talk. So I denote it as CT. It goes from X to R. It's defined by T of X is equal to alpha CT of X. Okay, so here, this was the definition of the being in this full group. And you see that by freeness of the flow, this T is actually unique. And this CT of X is just how to move from X using your flow from T of X. So, and you have a kind of I mean, it's called a cocycle because you have the following identity. So you have that CTU of X is equal to CT of Q of X plus CU of X. Okay, because if you go from X and you do this TU, then you first do U, so you're translating by CU of X, you arrive at U of X, and then to go to TU of X, you have to translate this time by CT of U of X, because you are now using T, okay? So you have this identity, and I just want to point out that which takes T to CT, it embeds this orbit full group into the space F0 X mu R. So the space of R valued maps from X to R, but you identify such maps up to measure 0. Okay? And this is an embedding. And what we showed with Alessandro is that this guy is Polish for the topology of convergence in measure, which is the natural Polish topology that you can put on this guy and which you probably are familiar with. If you're not, it's okay. That's just a comment I want to. So, okay. Now let's move to the thing which captures much more. So L1 full groups. Well, you may guess what's the definition now. So we are just, so the L1 full group of alpha is just all the guys in the full group, such that their cocycle, now you don't want it to be any measurable function, you want that CT is in L1. Okay, before I had L0, now I replace it by L1. So I want the cocycle to be integrable. So using this cocycle rule, you can show that this is actually a group. And this uses the fact that the transformation is measure preserving, because you want to say that the integral of CT, or the absolute value of CT, is going to be of CT of U is going to be finite as well. So yeah, and so let me now state some results. So